Hi guys, how you doing? This is chapter 5, the states of matter, liquids, solids, and gases, mostly focusing on gases and solids. Um, and this is one particularly will focus on the ideal gas law. So states of matter, we have solids, obviously. They're closely packed together like a crystal. They are in a pattern, as you can see in this model. They're no freedom of movement. They are rigid, so they're stuck together like a salt crystal. Volume is definite, and the shape is definite, meaning it doesn't change. Where liquids, they are close together, but not as tightly as solids. They fairly random arrangement, depends on their interactions with each other. They have a limited movement in all directions. So they are moving, but they are limited based on their shape. The volume is definite, it doesn't change, but their shape does change depending on the container it holds. Gases, on the other hand, are very far apart, obviously. They are randomly arranged. There's no rhyme or reason how they move. They're free to move in all directions. The volume is indefinite, and again, the shape is indefinite. Sorry, my picture's in the way. All right. So you can see here, if you put a solid in a beaker, it will just fit whatever that solid was. Liquids will take the shape of it, of the beaker, and they're weakly bonded to each other, where gases basically are just in there as part of the whole surroundings. They fill the container completely. So if I put a beaker outside on this desk, and gas molecules, air molecules will be there. And they can be compressed very easily, meaning I can put pressure onto it and it will take the volume and shrink it. All right, quick introduction to solids. There's basically 5 different types of structures. You have simple atomic, meaning it's a simple atom. Simple molecular, we talked about that earlier this year, like hydrogen gas, oxygen gas, all simple molecular. Giant ionic, giant metallic, and giant molecular. So a hydrogen atom is atomic, so it's simple structure, but if you have them in diatomic form, the structure is simple molecular. So the difference between simple atomic and simple molecular is really just if it's a molecule bonded to itself or bonded to other atoms that are weakly bonded, that's simple molecular, where simple atomic is just the atom itself. Giant ionic is like a salt crystal. Giant metallic is any bond of a metal. And giant molecular are covalent bonding structures like diamond, graphite, and silica, or silicon dioxide, SiO2. They are very hard, big structures, and they are bonded through covalent. So you see here this little flow diagram. You have ionic, covalent, and metallic, and really the only difference between the covalent is you get different structures. You have network structures like diamonds, quartz, and then you have molecular structures that are simple like carbon dioxide or water or nitrogen gas, iodine, and then you have big molecules like DNA and proteins, polymers. Those are big, giant structures. All right, now we get into the good stuff, the gas structure. Molecules are in constant motion. They are moving randomly. They fit the shape of their container. So the kinetic molecular theory, basically of gases, is important to understand that molecules are randomly and rapidly moving, which makes sense. The distance between gas molecules is greater than the diameter of the molecule, which also makes sense. Basically means that the volume is negligible of the molecule, so mostly empty space. You don't have a bunch of gas molecules all together. there are no forces of attraction or repulsion between the molecules. That's important because once you start having attraction and repulsion, you start having interactions with them. Their volume changes and their properties change. The collisions are elastic, meaning once they make a collision, they'll that energy basically is not transferred completely, so it's just bounce off each other like billiards balls. And the temperature of the gas is related to an average. So average kinetic energy is based on temperature. So the molecules, as fast as the molecules move, the temperature goes up. So ideal gases, they support the kinetic theory. So mostly smaller molecules that don't interact are going to be ideal, where real gases, they will encounter with other things and they don't fit the description. So most ideal gases are smaller, like helium and neon, where more real gases are bigger because interactions start occurring with these molecules. Again, you don't want interactions for ideal gas because then you have other aspects that don't make the ideal gas law true. So ideal gas, volume depends on pressure and temperature. Pressure is just the force per area, and temperature is just the average kinetic energy of a molecule. So to be an ideal gas, you want to have no low pressure because that means the volume is very big. The more volume there is, the less interactions you're going to have with gas molecules. And you want temperature to be high because then the elasticity of the molecules is greater. You're not going to have them to be close together and form interaction. So once they have high temperature, they'll bounce off each other, and that's fine. Okay. Pressure, 1 atmosphere is considered room temperature and pressure. Again, you want high temperatures because that causes the volume to also increase, and then that causes the interactions to be less because you have more volume. So low pressure, high volume is ideal gas conditions. So what happens when they don't behave ideally? Real gases don't obey the kinetic theory. The reason why is they will have more interactions with each other. Okay, so real gases will have an interaction with each other, causing volume change, causing chemical change, causing volume change. And then if volume is not negligible, meaning you have very low volume, small, you will have more interactions with each other and causing less ideal conditions. So at high pressure, you're going to have more interactions and volume becomes significant. So you want volume to be negligible, meaning insignificant. So that's why you want low pressure. Okay, so at high pressure and low temperature, so non-ideal conditions, this is what happens to molecules. They close together. Okay, volume is not negligible, so VD forces are present, VDW forces. The attractive forces start to interact with each other. Pressure of real gas is lower than expected. That causes the VDW forces to have interactions. And then it also causes the volume to be smaller, again, causing interactions with each other. So ideal conditions, you kind of want to be a introvert, and where at non-ideal conditions, real gases, they're more extroverts. They'll have more interactions. All right, Herbert equation, PV equals nRT. Pressure is in kPa, volume is in dm cubed or liters. Gas constant's 8.3145. Temperature is in Kelvin, that's important. Oops, and number of moles is M. All right, so this is what we're going to do. We're going to see if we can do some practice problems on the board. So we're going to see that we do this. All right, so we have N 0.50 moles. Okay. And we have P to be in 150 kPa. Temperature is in 19, so we have to add 273 to that. (292 Kelvin). So once you plug in the equation, P is 150, volume is what we're trying to find, N is 0.5, gas constant 8.3145, running out of space, temperature 292. So volume should come out to be 8.1 liters. All right, so hopefully that's the right answer. And it is. All right, so let's move on to the next one. We have volume, grams, and temperature. So we're trying to find pressure. So we have to do one conversion for moles. 4 grams divided by 32. That's 1/8. 0.125 moles. Volume is 5 liters. Temperature, add 273 to 127. 400 Kelvin. And plug it in. So P is what we're trying to find. PV. Erase that. Volume is 5. Moles 125. Gas constant. And temperature 400. Multiplication. Divided by 5, so pressure is 83.1 kPa. Okay, we got next. Homework question. All right, so your first homework question is on page 76. Check out number 6. You want to calculate the volume for question A and calculate the temperature in Kelvin in question B. All right, another way to use ideal gas law is to find the molar mass of a substance. So it's not the most accurate method. It's more just calculation, where mass spec is a more accurate method. But basically, to find molar mass, you need two things. You need moles, you need grams. So you have to divide the mass by the moles, and you find molar mass. So in these questions, they usually give you the grams, and you have to find the moles through ideal gas law, and then do the division. All right, so workout example number 3, page 76. We have volume, we got grams of the gas, we have pressure and temperature. Calculate the molecular mass. Okay, so we need to find PV equals nRT. We need to find the N because we have the mass. So we need to change temperature to Kelvin, so it's 293. Pressure's in kPa, volume is in liters, so we're ready to go. 200 times 2 equals N, gas constant, and temperature. Plug it in. What do we get? 200 times 2 divided by 293 divided by 8.3145. We get 0.164 moles. find molar mass, you take the grams, which is 528, divided by the moles, 164. And we get 32.2 grams per mole, which could be oxygen, right? 1660, yeah. All right, let's see what we got next. Oh, last homework question. We have 8.08 grams of a liquid X, and we have the temperature 100 Celsius with a volume of 23 centimeters cubed. And be careful there because you want to make sure it's in liters. And a pressure of 1.02 times 10 to the 5 PA, pascals. So again, you need to convert that to kilopascals before you do any work. All right, so let me know any questions, and we will get going to solids next. All right, signing off. Peace.